and he comes from the Colorado School of Mines.
Great.
Excited to learn more.
Thank you. And so just real quick, can you hear me and see my slides?
I can hear you and see your slides.
Okay, good. Hi, everybody. So thank you all so much, both to the organizers for inviting me to present during this and to everyone in the audience and to listening to me. So I'm going to talk to you today about the VSLQ design, which I originally came up with and was published back in 2016 and is an ongoing experiment with Dave Schuster's group. The way I decided to frame this talk was sort of to both present the basic idea and present sort of the key ways that it differs from the way bosonic error correction codes are typically run, with the hopes of maybe inspiring more discussion about how we can take some of the best ideas from both of these paradigms for future circuits. So, just as an outline, first I'm going to introduce the idea of the VSLQ, how it's basically designed and how it's operated. I'm going to highlight key features, and then I'm going to talk a little bit about the progress of our experiment. We have not gotten full error correction to work yet, but we're certainly hopeful about achieving that within the next calendar year. The sort of the big challenge, the set of hidden challenges that make this, tractable but tricky to realize. And so to sort of frame this, a key question that asked by many people in the field, like basically everyone besides Google and IBM, is how do we improve on the TRANSMON, right? A lot of groups are working very hard and doing amazing things, just scaling up. But there's the other field of thought that says, no, our qubits aren't good enough yet. We really need a much better qubit primitive. And right now, I think, the undisputed leader in scalability, at least, is the TRANSMON. And being just a Josephson junction and a capacitor, the TRANSMON can't be simplified. We can't make a simpler TRANSMON. So there are two ways to improve on it. Option one is improve materials, which is an enormous effort by many groups and should benefit lots of different circuits, not just the TRANSMON. And option two, since it can't be simplified, is to add complexity. And so I tried to sort of take every popular superconducting qubit idea I could find and stick it on one slide. And if you quibble with where I put some of these, please, this is just my opinion. For instance, I put the 0 pi, which is a subject of Andres's beautiful talk right before mine, in between new circuit elements and signal complexity, because gates on it are not nearly as straightforward as just on a single TRANSMON. The very small logical qubit design fundamentally involves no new circuit elements. It's just using them in a very different way. And so I put it entirely in the signal complexity side. Hopefully what sits in that question mark in the middle is the error-corrected fault-tolerant quantum computer that actually works. But I don't claim to know exactly what that looks like yet. So the very small logical qubit, the VSLQ, is a self-correcting logical qubit. So there is no measurement or feedback, whatever. Everything is done fully autonomously. The goal is to address all single qubit error channels in a compact, hardware efficient, and 2D implementation. If we could do it in 3D, obviously it would be better. But this is originally designed for 2D. And yeah, as I said, error correction is fully autonomous here. What it consists of is two detuned transmons. In our experimental design, they're about 1.5 gigahertz apart, with bridged grounds, and that bridged ground is critical, and a driven squid coupler. And the squid junctions are generally about half to the same order EJ as the transmon junctions. So fundamentally, all the VSLQ actually is a flux qubit with two resonators stuck on it and very fancy signal structure. So it's not, again, this is not actually a new design. It's just being operated in a very, very different regime. This was originally inspired by the 4-leg cat code. I originally had tried to figure out a nice, elegant way to do continuous autonomous error correction on the cat code. Couldn't come up with anything I liked and ended up with this. So that was the sort of origin of this idea. But that's important to say that the cat code was definitely what sort of got me thinking along these lines. It's continuously driven with a combination of 4 photon pumping that drives 00 to 22, so the or GG to FF for the two transmons, and 2 photon exchange, so FG to GF is coherently driven. And the 2 lossy resonators, or we could use qubits there too. It's just any object that dumps into its environment pretty quickly, is there for passive photon loss error correction. And so the VSLQ is designed entirely to fit the superconducting qubit noise model, and doesn't necessarily work for other noise models, but it should work very well for this one. So the TRANSMON, at least, noise model consists of 3 channels: photon loss, which is random relaxation of the qubit by losing photons in the environment. This is a roughly frequency independent power spectrum, and the solution is we're going to correct this. Photon addition, which is the random excitation of the qubit from thermal photons to the environment, and in a well-shielded and well-thermalized circuit, this is 2 to 3 orders of magnitude slower than loss, so we just ignore it. And then dephasing, which is the unitary non-entangling noise that comes from random fluctuations in the qubit energy. This has a low frequency dominated power spectrum. Our circuit is not complex enough to correct this, so we suppress it instead. And so just before I introduce the actual hardware, just as a quantum code, I want to talk about our logical state manifold. So our logical states are the 0-2 manifold analogs of X eigenstates, so 0 plus or minus 2, with the constraint that X left, X right equals 1. So the tilde operators are in the 0-2 manifold everywhere through this talk. So the 0 logical state is 2 plus 0 tensor 2 plus 0, and the 1 logical is 2 minus 0 tensor 2 minus 0. And the error model we are focusing on is just single photon losses. So if we have a loss in the right qubit, it sends us to either of these superpositions. And the key idea of the VSLQ is that the left qubit state here contains enough information to repair the loss error without distinguishing the parent states. So this is like the 4-leg cat code. This operates on a sense of sort of 4 parity, and that's sort of the minimal size you need for an error correction code. So like the cat code or the binomial code that followed it. So the components we will need is we need a Hamiltonian to generate this X left, X right operator in the 0 and 2 manifold. So this 2 photon exchange and 4 photon pump has to be always on. We then need a 2 photon pump or blue sideband couplings to ancillas for the photon loss repair. And finally, we need an energy penalty for the 1 and 3 states that keeps us in the logical manifold. Right. So this does not work if these are harmonic degrees of freedom, because you start mixing, I'm sure you could create a version of this that probably end up being like the 2 cat code or something like that. But this is the way that this is set up. It requires the anharmonicity. So this driven squid coupling is going to generate this XX term in the 0 and 2 manifolds. There are going to be blue sideband plus plus minus minus couplings to these resonators for photon loss repair. And the nonlinearity gives us the energy penalty we need for 1 and 3. So 2 transmons are coupled by a squid where there's a static flux, and I'll talk about this coupler in a little more detail. It's sort of, I think there's a lot of neat things to appreciate about this. We'll talk about this a little bit later. Basically, we thread a flux of pi over 2 or 1/4 quantum through the main loop and pi through the squid loop, and then drive both with AC fluxes alongside the DC offsets. And the tones are chosen to be commensurate with resonant 2 photon exchange and 4 photon pumping with the same amplitude and phase. And the larger nonlinearity allows us to mostly ignore states 3 and higher. You can't completely ignore them because they make some dispersive shifts and things like that you need to be pretty careful about tuning away. But so they're there, but you can sort of ignore them to this order at least. And so the VSLQ Hamiltonian for just the 2 primary qubits, left and right, in this rotating frame is literally just a minus W XX term, where W is the Rabi frequency, plus half the nonlinearity energy penalty for either qubit being in the 1 photon state. So that's the only Hamiltonian of the primary qubits. It's very simple. Again, we defined the logical manifold a couple of minutes ago. The logical operators are just any set that commutes with the Hamiltonian and anti-commutes with each other. So X logical is either X left or X right. Z logical is ZZ, the product of ZZ, again in this 0-2 basis. And Y is the product of X logical and Z logical. So error correction is done by a 2 photon pump coupling to these lossy elements. Chosen to drive things at exactly the right energy. That's why there's this shift W in the it's chosen to drive us back to the x left, x right equals +1 manifold and not the -1. If we do that, then we've, that's a leakage error essentially. So basically we're shifting the frequency of this 2-photon drive by the Rabi frequency of this term, this WXX term. And to give you an idea of how this works, so I'll walk through how the error correction process works for this. So the logical state manifold is stabilized by a coherent 4-photon pump and 2-photon exchange. The 2-photon pump couplings are coupled to lossy, what I call shadow resonators that are used for error correction. So give an idea of how error correction works. So initially we're in one of these logical states, and let's say we get a photon loss that puts us in a 1-photon state in the right. And this passively turns off the XX term by detuning, because again, the nonlinearity to the 3 state is much larger. So this is now suddenly far off resonant. Then what happens though is that as soon as we are in a 1-photon state, we now Rabi flop because of this always on pump coupling. We are going to now Rabi flop between the situation where we have a photon loss here, or where we've been sent the primary qubits back to the logical manifold and excited the resonator, right? So the resonance condition is that this is exactly resonant with repairing the error and exciting the resonator. But the resonator is lossy, so anytime there's a photon in there, it wants to leave, and it decays to its pre-error state pretty fast. And we can compute the repair rate here, so the error correction rate essentially analytically with Fermi's golden rule. This is a 2-step process. So as I just mentioned, the photon's transferred to the shadow object by this ++- term. Then it decays, and so it's limited by the slower of these 2 rates. But of course, the error correction couplings can't be too strong, or errors induced by the error correction mechanism will start proliferating and dominate the photon loss. And so there's this critical hierarchy of scales that if you've worked with any engineered dissipation scheme will look familiar to you. So the nonlinearity delta, which is a couple hundred megahertz, is going to be much larger than the XX term Rabi frequency, which we're targeting order 10 megahertz for, which has to be much, much larger than the 2-photon pump coupling and shadow qubit loss rate that should be the same order of magnitude. We're targeting around a megahertz for those, give or take. And then that must be larger than the loss rate in the primary qubits, which is 1/T1. And then provided that's all satisfied, we can find the repair rate and the logical error rate from this, gamma logical, and we can see that there's a quadratic suppression of the error rate. To give you an idea of what sort of performance we expect from this, so far we've talked about photon losses and just corrected them. And if that was the only channel, the only error channel, we would be done. But unfortunately, so these qubits have phase noise as well. And so how we deal with phase noise is by appealing to the fact that low frequency phase noise is passively suppressed by this XX term. Right, that essentially this is Rabi driving it fairly hard all the time. And so the phase noise is not seeing the entire 1/f power spectrum, it's sampling it at some, order 10, 20 megahertz frequency where we expect it to be weak. And so what we plot here on the right is the lifetime improvement for the X logical state against photon loss. So that's this T1, that's T1 down here, T1 primary, assuming both the qubits have the same T1 for simplicity, and 1/f phase noise. And so I chose to normalize this in terms of having the phase noise strength, the phase noise, the Ramsey T2 Ramsey, not echo and things like that, because that complicates things more. Compared to T1. And so for the top blue curve, there's no phase noise. For the gold curve, the Ramsey T2 is equal to T1. And then all the way down to the bottom purple curve, we have Ramsey T2 is 1/8 T1. And you can see that this is plotted as terms of T logical over T1. And you can see that this is roughly linear. Eventually it starts to get limited by other things. But you can see that this is roughly linear, proving that there is indeed a quadratic improvement. And estimating from this chart and realistic device parameters, I think for sort of default coherences, like what we can achieve in the Schuster lab and what is commonly achieved in other groups, it's pretty reasonable to target around an order of magnitude lifetime improvement for the logical states. You know, there will be other things that limit this, and I'll talk about in a minute, but like the nice thing about the VSLQ is because everything is being driven pretty hard and continuously, the threshold lifetime, you know, the threshold is pretty loose. Like you don't need to have very good base coherence to see a improvement. Obviously, the better your base coherence is, the more improvement you expect. It's an error correction device, but the threshold is pretty low here. And so that's what is promised, and that's just what we hope to achieve. And you know, a few things I want to highlight about this that, you know, beyond just the lifetime improvement. One thing is, and I think that this, you know, might be useful well beyond the VSLQ, is that this AC driven SQUID with bridged grounds is an analog universal coupling element. And what I mean by that is, in a gate model, any 2-qubit gate in single qubit rotations is universal, right? You can make any 2-qubit unitary by combining a few CZs and a bunch of single qubit rotations, right? But analog universal means I want to make any 2-qubit unitary now and instantaneously and have it evolve under some arbitrary combination of Pauli matrices. And you can actually do that with this, because this coupling turns out to be a direct nonlinear element that's not mediated by linear terms. And so the beauty of this is, so for example, if we bias this, let's say these two junctions are exactly equal. If they're close but not exactly, you can do a little fine tuning to fix that. We bias the SQUID at pi flux, so this is off, and the main loop at 0. And then basically there's a special trick where if you drive the main loop at an AC flux f of t and the SQUID at -2 f of t, then the only non-zero term left over from this coupling is the direct AC 1 and 3 photon coupling. So I can directly drive 3 photon processes, which would be in this case like adding 1 photon to one transmon and 2 to the other up and down, or 1 photon conditional, with a Z shift based on it. And those are the only things that show up. We've eliminated like all the static terms in doing this. And the same thing with the main loop bias of pi over 2, which is what we're going to probably use for the VSLQ. You can do the 2 and 4 photon couplings at first order, right? So I can get a 4 photon pump at first order from this thing. And, as I'm sure like any of you who've ever worked with any of this stuff are well aware, it's pretty easy to get the term that you want if you want some 4 photon process at some order in perturbation theory. It's very hard to get only that term, right? And there's other stuff that comes along for the ride can be very destructive. And so this is why I say that this is pretty much the sort of most flexible possible coupler, is that I don't know of anything that can give you these crazy high order processes at first order, and high order and photon number at first order in drive fields. The downside is that the grounds do have to be bridged. So if we were in this doesn't appropriate to like a 2D grid because you have flux quantization loop issues. But I think that this is a really exciting sort of element to really explore further. The other thing is that, as Liang already mentioned earlier, and I think a couple talks I unfortunately had to miss because I have no childcare right now, is because of the pandemic, is that the very small logical qubit design supports error-transparent logical gate protocols. And to make an error-transparent gate, we simply tune the operation so that the commutator of the photon loss operator and the gate Hamiltonian commutes when acting is 0 when acting on the logical manifold, right? And you cannot in general define a gate Hamiltonian that commutes with photon losses, but you can cleverly design this operator such that the commutator, what results of this, has expectation value 0, returns 0 acting on logical states. And if you can do this, then basically we can do our gates while having photon losses in the middle and then correct them at the end as if nothing had ever happened. And the reward for this is that gate error is reduced by a similar factor as idle error, right? And I would say that this protocol, whether you're using it in the VSLQ or a GKP code or CAT code or whatever, this is ultimately necessary for integration into topological codes, because lifetime improvement is not enough. You need a better 2-qubit gate. And this is a way to get there. So that's some of the promise of the VSLQ. Now I'm going to talk a little bit about the experiment and just sort of highlight where we are with that qualitatively and the challenges. So there are really two fundamentally hard things about making this circuit. There's some mundane hard stuff like we have to drive at a 4-photon frequency and stuff like that. But there are two sort of subtle challenges. So one is unprotected error channels like high frequency phase noise and random addition. We need our device to be very well thermalized so that that isn't limiting. We need our flux noise to be genuinely 1/f like and not tail off into some fairly strong white noise. And unwanted dispersive shift terms. So the VSLQ, so the unprotected error channels is sort of at the level of device and experimental design. And in our experiments, we've seen that up to the range we expect, our flux noise does look pretty 1/f. This is from an earlier iteration of the device, but it confirms that, yeah, this is decaying. So we will probably be limited by phase noise in the ultimate successful experiment, but not to the point that it keeps us from exceeding break even. However, the more serious concern is that the error correction process does not work if we have like always on ZZ or projector onto 1 times Z other terms. And the reason is all these terms enact rotations on error states, but not logical states. Or at least, well, the ZZ term enacts rotations on logical states as well. So you just want to get rid of that. But these P1Zs are the hard ones because they enact a rotation on an error state, but not a logical state. And since the time between an error and its correction is completely random, these are all logical error. This is this is an unprotected logical error. Fortunately, there's multiple ways to get rid of them. And I should say they have to be relatively weak, like order of megahertz. If they're pretty strong, then that just becomes a very tricky problem. But we can tune the static biases of the squid and coupler, or we could dynamically drive red or blue sideband terms off resonantly in addition to all of the signal structure that makes the VSLQ Hamiltonian, to generate a dynamical dispersive shift. And by choosing that red or blue with the appropriate detuning, we can completely cancel that dispersive shift. And we've tested that in the lab, and that does work. So it's a beautiful technique that's been used a couple of times before. So that's another option too. So just to talk a little bit about what we're doing with the experiment. So this is David Schuster's group, led by Jikun Lee, Tenai Roy, and formerly Yao Lu, who's now a postdoc at Yale. And we're making good progress. So the setup is we have 2 transmons, which are these two pads here, that sort of oval shaped things. The squid and bridge ground coupler is right in the middle, AC and DC flux controls, and it's capacitively coupled to these 2 resonators. The biggest challenge for us has been that early iterations of the device had very strong, order 60, 70 megahertz raw coupling, stray interactions between the qubits that were not coming from this squid, and figuring out where that came from and what was going on was quite tricky. So, we have a 3rd iteration of the device that's being sort of tested now and is hopefully going to be the final one. But what we've been able to achieve so far is consistent base T1s of 40 microseconds or higher, which is well above what we needed for break even. Phase noise with a definite 1/f character that's maybe a little stronger than we would like, but shouldn't keep us from a successful experiment. And we've managed to demonstrate, and we'll give a couple talks at March meetings about this and things like that. We've demonstrated all the interactions separately. This circuit is a significant filtering challenge as well, because you have to drive a bunch of very weirdly separated frequencies at the same time. And all the necessary interactions have been demonstrated, including the 4-photon direct drive at first order, which is right here. We've also done this dynamical dispersive shift cancellation and a direct ZX term, so essentially a continuous C0, just sort of to see what we can do with this. And when the stray interaction is sufficiently reduced, and hopefully the newest device will do that, because we think we finally identified what was causing it, we just need to combine everything and calibrate it and go. The very small logical qubit, as I said, is a very different approach to bosonic error correction. If you can get everything in the Hamiltonian to work properly, it's an order of magnitude improvement in lifetime with current technology. And I should say again that this is a very different approach. So this is a very fast, direct drives and low base coherence. Whereas if I think about a CAT code or a GKP code, these are slow and ancilla-driven interactions that are sort of abstracted and higher order, but applied to something with very high base coherence. And it would be beautiful if these things can be combined in some way, can adapt some of these VSLQ ideas to a 3D system, or to use something more intrinsically protected than a transmon as the base qubit. So this research is funded by the Army Research Office and the National Science Foundation. So I'll just go back to the sort of beyond the transmon slide and take a couple questions.
Thank you very much for the presentation. You couldn't hear my clapping. We have some time for some question. So Josh is asking about when we couple two of these very small logical qubits, are there any difficulties that will arise? And does the autonomous correction on both qubits make it difficult to do the 2-qubit gate?
No, so it doesn't. And so that was the whole reason for this error transparent gate idea, was to solve exactly this problem. And so the coupler between pairs of these things is a bit tricky to engineer, because you want to be driving things in the logical manifold, so these zeros and these 0-2 photon processes through a coupler. So designing the right coupler to do this, and in my 2018 PRL in this, I talk about a couple ways that we can do this in a couple different gate families. But so I'd say the challenge is making a scalable coupler between these more complex objects, and that's a challenge of things like CAT codes and other things as well. More than, the error correction itself doesn't interfere with the gates. It's more just that we have to do a scalable linked operation through higher order terms. And I mean, that's the same problem that a lot of these codes have. It's tractable, but it's definitely harder than like just doing an I swap between transmons or something.
Okay. So there seem to currently not be, now we got a question from Shruti, otherwise I would have asked one. Just a comment, not a question.
Oh, thank you. Yeah, I was happy to see that come out before we actually got the experiment to work on our own device. So yeah, it's really nice to see these ideas percolate in the community, and I hope that my hope in part was from this talk was to really have tunable couplers percolate into the community, because I mean everyone agrees that having just a transmon and ancilla is by far the limiting thing in these these bosonic codes, and that if we could get a tunable coupler in 3D that doesn't kill coherence, and so whether it's and so just showing what you can kind of do with these things if you can make them. And I accept that it's quite a coherence challenge to get that to work in 3D, but so that's kind of why the way I framed the talk in this way for that reason in part.
Yeah, so let's hope the field will give you the coupler you want. So Shruti is now finally asking a question. Is it possible? Yeah, sorry. Is it possible to have error transparent quantum simulations?
Yes, I don't see why not, because fundamentally an analog version would the only thing that's different between analog and digital is having these things on all the time versus pulsed, right? That's really, so in principle, yes, there's no reason why not. It would be tricky, but yeah, that's something I've thought a bit about more in the context of optimization, sort of like an RF annealing kind of idea or something, instead of because there's some beautiful proposals on doing annealing with CAT codes and things like that. But that's something I've thought more about. Josh asks, is there any advantage to having higher Fox states in the code or switching to a CV code word like a cat? So I should say I'm not nearly as well acquainted with the fine details of like the continuous variable states as I am with the discrete ones. But the one problem with using higher order states in these codes is that because of the nonlinearity, photon loss knows what level it was lost from. And that makes code design much trickier. So, you know, if I have a cat, you know, there may be some care effect that complicates this a little, but like a photon lost from a 3 state and a 1 state have very close to the same energy and doesn't distinguish them. Whereas with this, because it's transmons, they do. And that makes photon losses take a lot more information with them and makes designing higher order codes harder. I'm not saying it's impossible, but that I haven't figured out a good way to do it.
So yeah, thank you very much. So
Thank you.
yeah, I would be kind of curious about like going from like harmonic modes to qubits in a continuous.
Yeah, and anyone wants to reach out to me about that. Unfortunately, I have to leave because again, no childcare, and my wife has to teach 3 minutes ago. But anyone who's interested, please reach out to me. I'd love to chat about this further.
Okay, thank you very much and for
Thank
the
you.
talk. And I think now we have a 15 minutes break.